NASA says its Voyager 1 probe, the most distant human-made object in the universe,
In 1977, a small spacecraft left Earth carrying fragile electronics, limited power, and a mission expected to last only a few years. Nearly half a century later, that same machine still whispers back across interstellar darkness, revealing not only how far it has traveled, but how deeply human ingenuity can reach into the unknown.
Pick up signals from an extraterrestrial civilization.
To understand how a 1970s spacecraft still sends messages from beyond the edge of the solar system, we begin with the story of a signal so faint, it's almost a miracle we can hear it at all. The signal from the edge. If Voyager 1 could speak in human terms, its voice would be no louder than a whisper, barely audible, nearly forgotten by the distance. Launched in 1977, it now drifts more than 15 billion miles from Earth, farther than any human-made object in history. From this unimaginable distance, it continues to send back data, not through dramatic broadcasts or bold signals, but through a faint radio pulse powered by no more electricity than a dim household bulb. The signal, traveling at the speed of light, takes over 22 hours to reach Earth. By the time it arrives, its strength has faded to less than a trillionth of a watt, then reduced another billion times beyond that. Yet somehow, engineers on Earth still manage to detect this vanishing trace, decode it, and listen to what Voyager has to say. This isn't just a technical marvel, it's an emotional one. Every time Voyager's signal reaches home, it reminds us that something we built decades ago, with tools and knowledge far more limited than today's, is still out there, still working, still talking to us. But to understand how we maintain this fragile lifeline, we have to go back to how the journey began and why Voyager was launched in the first place. Building a bridge across the void. The 1970s were a time of bold ambition in space exploration. Following the success of the Apollo missions, NASA engineers turned their eyes outward, far beyond the Moon, beyond Mars, beyond even Jupiter. Their goal was staggering, to send robotic explorers on a grand tour of the outer planets. But there was a catch. The opportunity to do this would come only once in more than a century. In the late 1970s, a rare planetary alignment offered a cosmic shortcut. Jupiter, Saturn, Uranus, and Neptune would briefly line up in a configuration that allowed a spacecraft to use gravity itself as a slingshot, gaining speed from each planet to hurl it toward the next. This alignment wouldn't happen again until 2150. Missing it meant waiting a lifetime. Voyager 2 launched first, on August 20th, 1977, followed by Voyager 1 just 2 weeks later. Though Voyager 2 would ultimately explore more planets, Voyager 1's trajectory would carry it faster and farther. Each probe carried a 12-foot wide high-gain antenna, gold-plated audio records intended for any alien civilization that might one day find them, and an array of instruments to photograph planets, measure magnetic fields, and analyze cosmic particles. But perhaps the most radical part of their design was not what they carried, but how long they were expected to last. Engineers designed the Voyagers for a 5-year mission. That these spacecraft still operate today is not only a testament to their craftsmanship, but to a mission that never stopped evolving. Their journey was never just about planets. It was about pushing the limits of communication, endurance, and reach. Whisper power and the Deep Space Network. At the heart of this interstellar dialogue lies one of the most ambitious engineering feats on Earth. When Voyager 1 transmits data, using only 22 watts of power, barely enough to run a refrigerator light, its signal begins a long and lonely journey. It must cross billions of miles, stretch through the thinning edge of the solar system, and arrive at Earth as little more than a ripple in the cosmic noise. By the time that signal reaches us, its power has faded to less than a fraction of a trillionth of a watt, then reduced again by another billion times. That's equivalent to detecting the heat from a single match on Jupiter. To make this possible, NASA operates 3 giant radio antenna complexes located in Goldstone, California, Madrid, Spain, and Canberra, Australia. Each complex hosts a 70-meter, 230-foot wide dish, among the largest on the planet, synchronized in rotation with the Earth, to ensure Voyager is always within reach of at least one listening ear. These dishes don't just listen, they interpret. Through complex signal processing, they amplify the faint message, filter out cosmic interference, and decode the scientific data Voyager sends home. Even small adjustments, like accounting for Earth's rotation, atmospheric interference, or solar noise, must be executed with exquisite precision. The process isn't instantaneous either. What we received today was sent nearly a day ago. Behind each transmission are teams of engineers, analysts, and mathematicians who have kept this network alive for decades. This isn't automation, this is orchestration. They aren't just maintaining a connection. They are sustaining one of humanity's most fragile and most astonishing technological lifelines. The moment space rang like a bell. For decades, scientists speculated about where the edge of the solar system truly lay. Was it the boundary of the planets, the edge of the sun's gravitational pull, or the moment when solar wind gave way to the vast, charged emptiness of interstellar space? In 2012, Voyager 1 delivered an answer, not through a photograph or a signal burst, but through something far more haunting. Earlier that year, the sun released a massive coronal mass ejection, a solar storm of charged particles that took over a year to reach Voyager's location. When it finally arrived, the plasma surrounding the spacecraft began to vibrate, generating a phenomenon known as interstellar plasma oscillation. It was the first time we had ever heard the medium of interstellar space. In a sense, space itself rang like a bell, and Voyager 1 recorded the pitch. That vibration wasn't just eerie, it was profound. By measuring the frequency of those plasma oscillations, scientists at NASA and the University of Iowa were able to determine the density of the surrounding space. The data confirmed it. Voyager 1 had exited the heliosphere and officially entered interstellar space. The sound, transmitted across 11 billion miles and heard over a year later, was the first true echo from beyond our solar system. This discovery transformed Voyager's role from planetary explorer to interstellar emissary. It wasn't just observing space, it was embedded in it, using solar storms as sonar pulses to reveal the texture of the cosmic ocean. In that moment, Voyager was no longer just a machine. It became our listening post in the void. When things go wrong at the edge. Operating a spacecraft in deep space is not just a technical challenge. It's a slow-motion crisis management exercise. Every command takes nearly a full day to arrive, and every malfunction unfolds in silence. So, when something goes wrong aboard Voyager, there's no control panel to flip a switch, only patience, planning, and hope. In 2023, Voyager 2 experienced an unnerving moment. A simple 2-degree shift in its antenna's orientation, barely more than the width of a finger held at arm's length, was enough to sever communication entirely. At over 12 billion miles away, even the slightest misalignment turns the spacecraft into a ghost. For weeks, Voyager 2 drifted in radio silence. But this possibility had been anticipated decades earlier. The probe had been pre-programmed to perform periodic self-corrections. When that moment came, it reoriented itself, re-established contact, and the signal returned, faint but intact. Voyager 1 faced its own crisis. A software issue caused it to send data through a non-functioning onboard computer. Engineers at NASA spent months diagnosing the problem, working through ancient code and legacy documentation. Eventually, they issued a carefully crafted command, instructing Voyager to reroute its data through a working system. It worked, but the fix had taken nearly half a year to implement. These aren't just software bugs or mechanical quirks. They are reminders of just how fragile this long-distance dialogue has become. Every correction risks failure. Every silence could be permanent. And with each passing year, the list of systems that can be turned off grows longer, while the list that still works grows shorter. Borrowed time, fading light. The energy that powers Voyager's instruments doesn't come from the sun. Long before solar panels became standard for spacecraft, Voyager was equipped with 3 radioisotope thermoelectric generators, nuclear batteries that convert the heat from decaying plutonium into electricity. At launch, Each spacecraft generated more than 400 watts. Today that number has fallen below 200, and it continues to drop every year. To conserve what little energy remains, NASA has slowly shut down Voyager's instruments one by one. The cameras were powered off long ago. Now, only a few key sensors remain, those that measure magnetic fields, plasma waves, and charged particles. Even these will eventually go dark. Yet, engineers are not giving up. In recent years, they have extended the life of Voyager's thrusters by adjusting the duration of their firing pulses, reducing the buildup of residue that could clog the fuel lines. Still, time is closing in. By the mid-2000s and 30s, there may not be enough power left to transmit any data at all. When that happens, Voyager will go silent, not because it failed, but because it succeeded for longer than anyone dared imagine. Even in silence, Voyager will continue to drift outward, carrying its golden record through interstellar space. It will outlast Earth's civilizations, its technologies, and perhaps even the memory of the people who built it. But until the final watt is spent, the spacecraft will keep calling home. Long after we've gone quiet, Voyager will still drift, an ember of Earth in the cold dark, carrying questions no one may ever answer. But for now, it still speaks. So, if you're still listening too, hit subscribe and tell us, what would you send into the stars?